So here's the first one. Zachary tries to simplify the fraction 2020 over 5050 by dividing the numerator and denominator by the same integer to get the fraction m over n, where m and n are both positive integers. Find the sum of the not necessarily distinct prime factors of the sum of all possible values of m plus n. And so in order to do this, we'll notice, well, a first good step is to first figure out what 2020 over 5050 is. 2020 over 5050 is 2 times 10,010 over 5 times 2 10,010, which equals 2/5. And so really what's happening here is that we're going to get a bunch of fractions. And these fractions will all be of the form 2k over 5k. 2 times k over 5 times k, just to be clear, kind of looks like digits, where k divides 10,010. That's what's happening here. Take a moment to convince yourself of that when you're simplifying 2020 over 2050, you're going to get 2 times k over 5 times k, where k divides 10,010. And 2k over 5k, the value is still 2/5, and we also have k divides 10,010 because Zachary's dividing by an integer. Okay, and so now we're trying to find, so m over n equals this. So now we're trying to find the sum of m plus n over m over n that's legal m over n. So our answer is this. And this will also be equal to the sum of 7k for all legal k, which is k dividing 10,010. And this is equal to 7 times the sum of all k dividing 10,010. And now there's a nice formula for how to compute this. The sum of all the divisors, that's what k are. The sum of all divisors of 10,010 will be equal to, okay, I should first write out that 10,010 equals 2 times 5 times 101. Important factorization here. And so the sum of the divisors of 10,010 will be equal to 2 plus 1. And why is this true? Like why? It's kind of a big step. Why is this equal to this? This is a pretty general result, actually. And it's because we can build any k inside of the expansion of this. For example, can somebody name a divisor of 10,010? Actually, no, I don't know. Okay, so like, let's say like 101. What if you want to get 101? What if you want k equals 101? Then you pick up this one, and this one, and boom, they multiply out to 101. Let's say we want 10, 2, 5, 1. And so all of the factors of 1,000, all of the values of k will be generated in the foiling out of this. And so the value of this is just 7 times 3 times 6 times 102. And now we just have to do some arrangement. Notice that we want the sum of the distinct prime we want the sum of the prime factors. So this will be 2 squared times 3 squared times 7 times 51. I believe 3. Yeah, okay. And then so our answer will just be, so then our final answer will be 2, 2, 3, 3, 7, 51, which is 10, 68. So the sum of the prime factors of that is 68. And so our main step, one of the hardest steps here, is this thing. Alternatively, you could just list out the prime factors, but that makes it a lot harder to factor at the end here. Good luck spotting that. And I guess I'll take a moment to explain this identity in general. So if we have some n equals, I'm going to try and be better about posting handouts explaining helpful ideas. Okay, I got another factor of, oh, shoot. Yeah, that's awkward. 51 equals 2 times 17. I can't do computation anymore. Okay. Thank you for that. Thank you for pointing that out. So yeah, in fact, our sum will actually be will actually be 37. Unfortunately, I kind of just went to here, and as you can see in my PDF, actually, in the PDF I wrote, that's just like an outline of the solutions. I got to here and I just used the calculator to get the number. I didn't look at the answer formatting. So yeah, the actual one, 37 seems 24, 53. Okay, yeah. So the sum of prime factors is 37. Okay, and so I'm going to prove there's a more general version of this, which, yeah, okay, I will do it. Okay, so if n is equal to p1 to the e1 times p2 to the e2 times p3 to the e3 and so on, then the sum of the divisors of n, I think this is actually pretty helpful. Like you can, like there's going to be a lot of problems like this where you can theoretically do enough computation to get it out. But a lot of the times when people make silly, quote unquote, sillies, it's usually because they used a not great method, which requires a lot of computation, where there's actually a much cleaner method. So for example, for some n like this, for some general n that's prime factorized, the sum of the divisors will be equal to p1 to the e1 plus p1. That will be the sum of the divisors of n in general. It's kind of the same idea as before. Okay, so firstly, all numbers in the expansion of this will clearly be a divisor of n because it's just like the exponent. The exponent of like this is less than the exponent in here. And then there's the same number of terms. And so the expansion of this will line up with the divisors. And so that's a very powerful technique if you ever need to calculate the sum of the divisors. All right,